Welcome back to my channel for another video on microcontrollers, this time on Raspberry Pi Pico, which is a much more powerful microcontroller than the Arduino group. We'll see a little more about it. Here is my new Raspberry Pi Pico. This is different from Raspberry Pi 5, which I had shown earlier. Raspberry Pi 5 is a single board computer, while this one is not a computer, it is a microcontroller. Pico series are microcontrollers. If there is a designation W, that means it will have Wi-Fi. This does not have that designation. And this is the cable which I got, a USB micro cable over here. The other plug is just standard USB. This came along with this, and it is coming from the authorized distributor in this region, RoboCraze. Inserted the micro USB cable into the socket just to see that it fits well. Two varieties available. One with headers soldered. You have the headers pins over here soldered on both sides. I thought I might try this out because this will be suitable for mounting on my breadboard. That's what I presume. While the other one comes without these, just plain board for soldering. And I'm not very keen to solder on such boards. That's why I ordered with headers. You can see the nice Raspberry Pi logo here. This is a magnified view, and name is there, Raspberry Pi Pico H. H should mean with headers, and copyright year is 2021. And this is the boost cell which you have seen here, and USB port is there, LED is there. And this is the processor. This is the main processor seen over here. You can see that very well. Now, even without a spotlight, I am able to see. Usually, I see all these chips by using a spotlight. Somehow, it's seen well even without a spotlight. I got this one at a higher cost than Arduino Nano in this region, but this is supposed to be much more powerful chip than Arduino Nano. This is the boot cell button in Raspberry Pi Pico. It is important to choose the mode when you connect this device to a computer. I'll show you. When the boot cell button is kept pressed, when the device is connected using a micro USB to USB cable, then it enters the mass storage device option. It has been recognized as a mass storage device RPI-RP2D with you can see it is like another hard disk pairing in my computer, and that is with 127 MB free of 127 MB. This is done when you want to install a software first. Connecting to the computer with boot cell button pressed gives the bootloader mode for uploading firmware in Raspberry Pi Pico. That mode allows us to upload new firmware like MicroPython to the flash memory of Raspberry Pi Pico. After uploading new firmware, we have to disconnect and then reconnect the Pico without pressing the boot cell button, and it will boot into the standard application mode for running programs. In the standard application mode, the program which was previously uploaded allows the Pico to perform its intended function. As I mentioned in the unboxing video, these are the pins or headers which have been soldered in my version. If these pins are not there, then it is the castellated board which will have only holes, half holes, for which there will be the coating, and then you can connect it to other boards. This is not like that. This is meant for mounting on breadboard, which is more convenient for a person like me who is starting off with Raspberry Pi. The pins are numbered starting from this side, that is the place where you have the USB connector, and from that side 1, 2, it is numbered like that, and on the opposite side it will be numbered from 21, and totally there are 40 pins. And the interesting part here is that you have several ground pins here. This pin 3 here is a ground pin, then there is 8 ground pin, 13 and 18. These are ground pins. On the opposite side there are similar ground pins. They are numbered there. All the numbers are not given. You can see 23, then 28, then you can see 33, then 38. 38, the number is not given here. Here it is 39 is given. So 38 is a ground pin. The ground pins will be 3, 8, 13, 18 on one side, and on the other side it will be 23, 28, 33 and 38. They are the ground pins. The other pins on this side are numbered as GP0 from the other end. From this end it is GP0 and GP1 and so on. At this end it will be GP15. This will be GP15. On the opposite side we have pins which start from here. This end starts as GP16, 17 and so on, and it will go up to GP28. Pin numbers are up to GP28. The two pins beyond the ground pin, that is 38, are VSys and VBus, the last two pins. Then 37 will be 3V3EN, and just before that 36 will be 3V3 out. That's 3.3 volts output as you have in Arduino. Arduino has output at 3.3 volt and 5 volt also. So fifth pin from the other end, that is it, 1, 2, 3, 4, 5. This will be that pin, 3.3 volt. This pin is ground pin, and 29, 30. 30 will be another pin which is known as run. So these are the markings, or rather identifications of the pins, though all of it is not written on the board. There is also an onboard LED which you can see here. LED is connected to GP25. So you will find that missing on the other side, where you have the run pin is between 22 and 26. 25 is not there. Next step is to install a software known as Thorny, which is free and open source. Integrated Development Environment IDE for Python that is designed for beginners. You have to go to thorny.org and download the file. After downloading Thorny from thorny.org, I have just connected this Raspberry Pi Pico H. H means with header pins, using a micro USB to USB cable to the laptop. Connection was done holding down this pin, this button, that is the boot cell or boot selection, which selects the mode of booting. And once that is done, this will boot into the bootloader mode or mass storage device mode, so that this will be shown as a separate drive in my laptop. This is the additional drive seen in my laptop, RPI-RP2 as additional disk D with 127 MB free of the 127 available. And this is the downloaded file thorny.exe, thorny 4.1.7.exe, which I have brought to the desktop. I'm going to install thorny 4.1.7.exe. Of course, you have to accept everything, otherwise there is no way. I'll also create a desktop icon. Installation onto the laptop is quite fast. And that's over. This is the desktop icon. I'll just open. This is the Thorny window. In this Thorny window, there is the interpreter on the local computer, that is local Python 3 Thorny Python, that is Thorny's Python. And I'll have to click on that. And options are shown. Install MicroPython. That's what I want to do. And the target volume is not the laptop, but the Raspberry Pi Pico, that is RPI RP2. That is what it is to be selected. And version, I can choose Raspberry Pi Pico H because this is Pico H. And the version has automatically come there. Now I'll click install. This might take longer time. No, it did not take. I thought it will take longer time because it's onto a smaller drive, but it was done very fast. So that has been installed. So next time I want to run this, I don't have to keep the boot cell button pressed. If I keep it pressed, it will again go into same process. Now I have connected Raspberry Pi Pico in the standard application mode so that it will not come as a disk in the computer. Only hard disk C will be seen. D is not seen now. And I opened Tony again, and this is the shell lower part you can see. Hooray! I have been able to start the LED blinking in Raspberry Pi Pico. You can see that the green LED is blinking now, and I'll tell you what I did. I took a code from ChatGPT and pasted it inside the uh, editor. I'll show you that. This is the code which ChatGPT told me for making the LED in Raspberry Pi Pico start blinking. And the code is from machine import pin. This P should be capital. Earlier I put it small letter and it didn't work. Import time LED is equal to pin 25 pin out, while true toggle and sleep 0.5, that is 0.5 second is the wait time. And as soon as I pressed enter and then I did this run current script, then this will appear and it will start blinking, and you can save this as a sketch, save a copy to Raspberry Pi. But now I can't do it because this is busy. Earlier when I saved, it worked. That's quite interesting. Then I'll see if I can change this timing. Instead of 0.5 seconds, I'll make it say, let us say, few seconds. And let me see. Run current script. Now, after changing the timing from 0.5 to 2, you can see that the blinking speed has come down. So it is quite slow. After changing the timing from 0.5 to 2, you can see that the blinking speed has come down. So it is quite slow. NEMA 17 stepper motor is widely used in robotics and 3D printing projects. Unlike the usual direct current motors, it moves in small steps depending on the signals given to it. Hence, it is possible to know its position without an additional sensor. A driver unit like A4988 is needed to drive the NEMA 17 stepper motor with a microcontroller. A more powerful driver is the DRV8825 driver, which I have not purchased yet. A4988 driver has features like adjustable current limiting, protection against overcurrent and overtemperature, and the facility to choose among 5 micro-step resolutions. It can operate with a wide range of supply voltages from 8 volts to 35 volts. About 1 ampere current can be delivered without a heatsink or forced airflow cooling. With heatsink and good cooling, A4988 driver can take up to 2 ampere current per coil. The driver supports full, half, quarter, eighth and 16th step modes of operation. Though there is a thermal shutdown circuitry, there is no reverse voltage protection for A4988 driver. A4988 has been photographed with the heatsink so that the processor is not visible. Here is the photograph taken before the heatsink was fixed. Image has been inverted so that the processor name can be read. The preset potentiometer is seen at the top in the second image, while it is at the bottom in the first image. Both these are magnified images. VMOD pin at the top can be used to supply power for the stepper motor, which may range from 8 volts to 35 volts. Pin adjacent to that is a ground pin. Lowermost pins on the same side are the VDD, which drives the internal logic circuitry running on 3 to 5 volt. There is a ground pin near that as well. MS1, MS2 and MS3 pins on the opposite side are the micro step select pins. If all the three are set at low or 0 voltage, the stepper motor works in full step mode. If all of them are set at high, then the stepper motor functions in the 16th step mode. Other permutations and combinations permit use in the other step modes of the stepper motor. Below that, there are step and direction pins. Step controls the micro steps of the motor, while direction controls the spinning direction of the motor. Remaining pins on that side are the enable, reset and sleep pins. Low input to the enable pin enables the driver. Low input to the sleep pin puts the driver in sleep mode with minimal power consumption. Low input to the reset pin causes it to ignore step inputs. It can also reset the internal translator to the initial stage of the motor. Remaining pins on the other side are the 4 output pins 2B, 2A, 1B and 1A. They can be connected to any bipolar stepper motor with voltages between 8 volts to 35 volts. The number 17 in the name of NEMA 17 stepper motor refers to the dimensions of the faceplate, measuring 1.7 inches on each side. This motor moves in steps of 1.8 degrees with 200 steps for a full revolution. NEMA stands for National Electrical Manufacturers Association, which brought out the specifications for stepper motors. Larger stepper motors will have larger number. Though there are 6 leads coming out of the NEMA 17 stepper motor from 2 coils, 2 of them are center taps and I have not connected them here. Other than checking continuity, integrity of the coils can be checked by connecting an LED across them and rotating the shaft manually, which causes the LED to light up. This particular motor has a gear fitted on the shaft. I use the circuit diagram given at howtoelectronics.com. First, the 2B, 2A, 1B and 1A pins of the A4988 driver were connected to the 4 wires from the stepper motor. They are the pins for driving the 2 coils in the stepper motor. 100 microfarad decoupling capacitor was then connected across the stepper motor power supply. That was across the VMOD and ground pins of the A4988 driver. Next, those 2 pins were connected to a 12 volt battery using a couple of jumper wires. G16 pin of Raspberry Pi Pico was connected to direction pin of the driver and GP17 pin to step pin of the driver unit. They are the pins for controlling the direction of stepper motor rotation and the step. 20 microfarad decoupling capacitor was connected across VDD and ground of the driver unit. That is the connection for the 5 volt power for internal logic circuitry. These were in turn connected to the V bus and ground pins of Raspberry Pi Pico. The 5 volt power was obtained by using a 7805 voltage regulator IC, which would step down the 12 volt battery power supply. MicroPython code for basic stepper motor control was obtained from the howtoelectronics.com page and pasted into a Thorny window, just as I had done for the previous blinking example LED code. Then I clicked on Run Current Script in the Run menu of Thorny, and the stepper motor started moving in tiny steps. This is the first step in my future project of getting an antenna rotate according to computer code. I know it is a long way off, but I do dream of getting my Moxon Yagi for satellite operations controlled by a stepper motor and G-Predict software in the long run.